Computer. Okay. So I did record the first lecture and I uploaded it, but I neglected to put the playlist up last night. So I just realized, wait a second, I'm missing the playlist for the recording. So I'll be sure to put that up as once class is done. Now, I want to talk a bit about strategy here for the Fox and Rabbit program. Okay. So at about 11:45, I will give you the answer to the goal, which will hopefully do that. So basically, we've got basically two strategies. Okay. So the first is like we've got this, so the second strategy is what I'm going to start with, which is that we've got some bush here, right? I know I'm really bad at drawing. It looks like a little four-leaf clover in the program. Okay, so anyway, you want to get your rabbit over here, and the idea here is that you can kind of do an infinite loop around it, or you want to get your rabbit here. It doesn't matter. The idea here is that we can kind of just do an infinite loop around this bush with the fox chasing us. That is the idea of the second strategy, right? However, it does have some issues here. The second strategy, what makes it difficult, which is that we could have a second bush over here, right? Or we could have a second bush like this, which could be less of an issue unless unless that impedes the direction we're actively trying to turn. Or the bush could be up against the wall. So this is what makes the kiting strategy a bit more difficult to perform. So instead, I recommend you work on the first strategy, which is to exploit the line of sight of the fox and the rabbit. Okay. So suppose we've got our fox here, and we've got our rabbit over here. Okay. The first thing to recognize is that if the rabbit is essentially staying still, then let's look at the fox's move. Okay, if the rabbit is just staying still, like he's got his default action is to just stay put, right? The fox looks around for the rabbit. He doesn't see it because there's a lot of space between him. There's no direct, grid line of sight to see. And if the fox is going this way, he'll step right over here. Okay, which means once he's there, right, he ends his turn, but he hasn't seen the rabbit yet because you look and then you decide where you're going to move. Once you decide where you move, you don't take any action after that. Make sense? Right? Your turn's over once you move. So if that happens, if the rabbit's staying put, he has the chance to see the fox before the fox sees him and react. So if he moves out of the line of sight, because the line of sight is move the rabbit a bit for the rabbit. So rabbit's over here. Line of sight is like this, right? The fox can look this way as well as this way. So I just have to move like into this, big triangle, this big cone, which acts as a giant blind spot for the fox. Or I move into this one. Make sense to everybody? Right? So basically just stay put until you see the fox, and then you can move away or move out of the line of sight. Now the first thing I want you to do is to try not that, but instead just try to directly move away. Now the issue with that is that if you see the fox moving directly away from it, and it's generally a terrible strategy because you'll just simply keep going and running until you hit a wall. And then you'll stay put at that wall, which does not bode well for your chances of survival. So you'll want to move out of the way somehow, be it this way, this way, this way, or the same, same moves in a symmetrical dimension or symmetrical direction, I should say. Okay. And believe it or not, just doing this can get you pretty easily into the 90% survival rate, 89, 90% survival rate. So question is, how do you So where's the failure cases? Well, the failure cases are when you get stuck and because you're too close to a wall and essentially bad luck. So how do you get above 90% survival rate? Well, the first batch of code that I explained for to get you to a 90% survival rate, if you do it correctly, that should take you, 12 to 15 lines of code, not too much, depending on how you code it. Once you figure it out, it's pretty nice. But the other ones is it takes more lines of code. And so what does that involve? Well, what you want to do is that if our rabbit hasn't seen the fox for a few turns, right? Then it might be safe to move a bit, just a bit, okay? And you only really want to move if you're too close to a wall, right? So the idea here is look around and say, hey, how far am I to the wall this way? Oh, there's not a wall there. Well, I don't know, right? What about this way? Or any direction, right? Just look any direction until you have a wall, until you see a wall. And you go, aha, I'm like 2 spaces away from the wall. Maybe that's a bit too close to the wall. And so you push away from that space, essentially. You go in the opposite direction of the wall. Make sense? But you only do that if you're like too close. It raises it a bit because there's this trade-off you have, which is pushing yourself away from the wall, but then you're also moving, which can give the fox the chance to see you because you moved into his line of sight. It's kind of a trade-off that you don't want to move too much. And that's also why you don't want to move, you don't want to push off against the wall just any time. You want to only do that if you haven't seen the fox for a while, because if you don't have that clause in there, you'll try to push off from a wall while the fox is actively chasing you, which could push you into the jaws of death. Not really a great strategy. So again, you want to get your base strategy working first and then go on from there. So what should you do? What is the goal? So for the next 35, 40 minutes, I want you to basically get the basic framework for this, which is write code for the rabbit that detects the fox. And if it sees the fox, do the stupid thing and move directly away. Once you figure out how to move directly away from the fox, it's not hard to figure out how to move something at some direction that's not directly away. The key to this is the model.turn function. So turn takes in a I and some number, okay? Some amount. And that amount, let's call it X, is the number of 45-degree turns. So for instance, if this way over here is I, okay, I and 4 would be 4 45-degree turns. So 1, 2, 3, 4, it's that way. Make sense? It also works negative as well. So if you did -4, like that. And if you accidentally overestimate, go around, it handles the modular arithmetic for you. So you don't have to worry about trying to do any modular arithmetic there. But it's the number of 45-degree turns. Utilizing that is pretty straightforward. And you should get to that point at least at the latest by like 11:50. Once you're there, and if you're not there yet, I'll show you how to get there at all. But otherwise, I'll be going around to the class and helping. Yes.
Do you recommend waiting, or you try to move away from an edge?
Probably 4 or 5, I would guess. I mean, the longer you wait, again, it's a trade-off. The longer you wait, the safer it will be, but the less impact it might have. So,
What is I here?
I is the direction. I is a given direction. Because if you don't use model.turn, what's going to happen is that you're going to have 8 clauses, which is that if that is to the north, then I have to move south. If it's to the east, I have to move west, right? And that just gets, so you'll end up writing 8 times or more than 8 times as much code as you need. And then also spending a lot more time on it because you'll have to figure out, for everyone, you're going to have to mentally check, okay, what is the opposite of each direction? Or what is the opposite and away from that direction? Okay. So stop share. And let's go ahead and. All right, so I'm going to resume recording. I think people have gotten close enough to the solution. So, or gotten close enough. So I'm going to go ahead, and if you're stuck, I'm going to kind of show you what direction you should be going in. Pun unintended. So over here, we've got our decide move function. Now for the rabbit, our default behavior is that we want to stay put. And as you probably discovered, staying put is basically the model.stay direction, right? So again, the way the decide move function operates is that you are telling the model what direction you want your animal to go. You can't directly move the animal yourself, because if you could just simply move him out of bounds. And that's not what the game wants you to do. So you tell the mob, so you're telling basically the program what direction you want to do. If it's an invalid move, it's gonna just tell you to stay put. So the only real part of the fox that we really care about is this over here. And not even what's inside it, just this loop, which I'll rewrite over here, which is what we want to do is that we want to look in every direction, and if we see the fox, that basically just check if we see the fox by looking every direction. So the way we do that is if in I is going to be the direction, is model dot min direction. Let's go ahead and get that shrunk down. I is less than or equal to, very important, by the way, that you do less than or equal to. It's a very common mistake is to leave out the equal sign. And so you're doing model dot. So you're only going up to max up, but not including the max direction. So you're going only 1 through 6. So. Oh yeah, I'll fix that. Oh, that max direction. Okay. Or there we go. And then that was totally intentional. I was just testing all of you. All right, so for I is equal, so basically this iterates through all the directions. This basically checks all the directions from north, then it goes northeast, then it checks to the east, then it checks southeast, then it checks south, then it checks southwest. But we really don't care what specific direction is. What we care about is that if I look in the direction, let's see, can I like get this out of the way somehow? Yeah, because you're having to peer around this, aren't you? Is that better? Okay, so look. So we're going to look in direction I. So given a direction, it returns a number corresponding to what is in that direction. So if I see the fox, so if look returns model.fox, which is a 1, but we don't have to remember that's a 1, we just put in model.fox, then we've detected the fox in direction I. We know he's in direction I, we don't know how far he is. Honestly, we don't care how far away he is at this kind of state. We might care later on, we might care if we're trying to be more intelligent about this, but we're not. And so basically what we're going to try to do is that we are going to move directly away from the fox. Okay? Which we can do by returning the number we want to move. So we know that he's in direction I. And so we could like add 4 to that direction to, because it's compass directions. So, right, if we're trying to go this way, we go this, that's 4 directions, so directly away. Right? But honestly, modular arithmetic is hard, so that's why we use model.turn. Return model.turn I and 4. Okay. So let's go ahead. So this actually will not do that great, to be honest. It's actually a pretty terrible strategy. But what it's worthwhile is, what this is worthwhile about is that I run the grader. First off, it works, it doesn't crash, which is always a plus, right? Oh, okay, I got something. Oh, I survived 1% of the time. There we go, which is better than 0%. So yes. But if we run rabbit hunt, we can actually see and confirm for ourselves that this is running, that we're actually so the rabbit is going to stay put. Let's go ahead and stop this one. That's not going to be a good example, right? There's actually very hard to find a good example there. So let's go ahead and run this. So now what we're going to see is we step. And so as soon as the rabbit sees the fox, he's going to go directly away like that. But since he's still in the line of sight, the fox is going to chase him until he hits a wall. So what's going on here in that part where he just stopped moving is that he's returning go directly away from the fox, which would work if this was Pac-Man world, where basically you go off the end of the map and you come back on. But this is more like Fortnite, where you're on an island, and although it doesn't shrink, I guess. So so you're in a bounded area is the point. So what you want to obviously do is A, probably not move directly towards the fox, and B, have some alternative ideas, because if you can't move in one direction, maybe you should move in other directions. So the key to that is using basically this statement before you try returning, which is if can move. So given a direction, can I move in that direction? Okay. So if I can move in a desired direction, then move in that direction. Otherwise, try moving another direction. Actually, you don't even need an else because it's returning. You just do repeated if statements in there. But rather than going directly away, try something else. In fact, the numbers might surprise you as to how effective that is. Because again, just running directly away was giving us a 1% survival rate. I mean, one thing you don't want to do is move directly towards that guy. Right? Or just returning I, which is directly towards us. This essentially returns I, and that gives us a survival rate of zilch, because you're just actively running into the jaws of death. The only reason we're surviving here, why we're getting any 1% survival rate, is because by staying put, there's about a 1 in 100 chance that he's not finding us. And that's pretty much what's going. And so we got about 333 over there. And running away doesn't really increase our chance. Running directly away doesn't really increase our chances. It does a smidge, right? 392 over there. Closer to 400 there, as opposed to 300. And the reason for that is that by running directly away, as opposed to running towards him, sometimes he detects us so late in the game that surviving for a few more turns is enough to run out the clock. But we don't want to run directly away. We want to run away from the line of sight. So what's a direction that's outside the line of sight instead of 4? Let's try 3. Survival rate is 17% now, because a lot of times you're able to just simply get out of his line of sight. Now, you can't always get out of the line of sight, because guess what? If you're trying 3, sometimes you're going to collide into a wall. Now, here's the relevant bit that everybody should listen to, even if you've gotten pretty far in the program. Am I going to have the same performance if I do 5? You'd think that. It's actually what I thought for like the longest time. And I couldn't figure it out. But for some reason, you get actually much better performance if you try going left rather than right. And I'm pretty sure the reason has to do with the Fox code, where he's got a bias towards when he's got an obstacle while he's moving, he's going to try to go around that obstacle in a very specific direction. Make sense? Right? He's going to try going, if he sees an obstacle in his current direction, he's going to try to go to the right before he goes to the left. So he always tries one of those things. If he chose at random, I think we wouldn't see anything. But because we always know that he's going to, when he paces around something, it's going to change that up. And look, he's using the model, the can move model.turn that I was talking about. So anyway, with that, you should actually be able to build a very effective strategy. Beyond that, you got to start taking into account the walls, other than the can move. The can move takes into account the walls and bushes. So let's see where you can get in the next 30 minutes. Okay.